Hello all, welcome to the video series on SIPI by EFR Engineer. In the last video, being an introduction video, we have discussed that all the SI problems can be timing, EMI or noise related. And in this video, let us see further related to noise and other topics. So first, let us take pipe and water analogy. If the pipe is not in good condition, then all the water will get leaked. Similarly, if the wires or interconnects are not good, the signal traveling in it also will degrade. So that is why signal integrity analysis is very important. And when we do the signal integrity analysis, we hear a lot of terms like ground bounds, skin depth, ringing, ISI, crosstalk, loss, etc. All these terms may be confusing at first instinct, but if we know what are these terms and what is the main source of these issues, then if we found the answer, then it will be very easy to do that in our design. So mainly all these issues are mainly related to the electrical properties of interconnects. So suppose this is some an image where a capacitor and an instance is connected through interconnects or wires. So if you see this wire, right, so this wire will be having electrical property, meaning a wire has RLC properties, and these are the properties which affects the propagation of the signal in the interconnect. All the signal integrity problems can be put into one of these four buckets. So it can be the signal quality of a single net, or the crosstalk between two or more nets, or we'll be having power and ground rails in the ship. So it can be the rail collapse issues in the power and grounds, or it can be EMI issues. And now let us first focus on signal quality of a net in this video. So suppose here is a voltage source we are having here, and we are putting signal into this trace. The signal will be traveling along with this trace to the receiver. So when the signal travels, it continuously asks a question, what is the impedance I'm seeing? If it sees the same impedance like all along the trace, then the signal will reach as is without any losses to the receiver. But if there is any impedance change that we call as discontinuity, then some of the signal will get reflected, and the rest of the signal, obviously distorted one, it goes to the receiver. And the main rule of thumb we follow here is the return path for a signal is important as the signal path. So it is very important to design the signal trace and the return path, that is both the traces or interconnects with as minimal discontinuities as possible. So since we know that impedance is the major culprit affecting the signal quality of a net, let's look into the parameters which affect this impedance. So you would be having somewhat idea like what are the parameters affecting the impedance. So I have listed it down here. So they are like any width changes or thickness changes or cross section changes for a wire, and the layer change through a via. It is like if a signal is propagating in particular layer, and if it sees suddenly a via on its path or nearby, then it is also considered as a discontinuity, or the gaps in the return path. And the most famous discontinuity is the end of a net. So all these parameters, like it affects the impedance, and this impedance it affects the signal quality. And there are some ways how we can design the signal race as a constant impedance line using some equations and all that as a designers they take care. And since we have seen one of the major culprits of signal quality of a net, let us see some more parameters. So this is a cross section of a metal stack. So here we have conductors and dielectrics, again conductor, again some dielectrics. So the signal quality, it depends on the conductor losses and the dielectric losses also. So suppose say a signal is on metal 2, like the metals being conductors will not be perfect at higher frequencies. At higher frequencies, they may have conductor losses, skin depth issues, and all. So these conductor losses also affect the signals, and the dielectric losses as well affect the signals because they are not the perfect isolators. And one more thing is the skew. Suppose say a signal is on metal 2 and a clock is on metal 3. If both of them have perfect skew. That is, if the clock reads the signal on time, then it's not a problem. The data will be read properly. If because of the skew issues, the clock is unable to read the proper data, then it is loss of information. So this is skew. Majorly, it is timing related, but it is also related to the electrical properties of the trace or interconnect. The skew majorly arises from the mismatch in the lengths of the interconnects. So these are the four things that we need to keep in mind while designing a trace for the signal. So that's all for this video. Thank you so much for watching. Stay tuned for other videos. If you have any doubts, please visit www.logicssoc.com or mention in the comment section. Thank you so much.